one.
All right, this is the DIC tensile testing with Blake, Mario, and Eric, showing just how three materials are deformed. In this lab, we are testing how three materials are deformed, and the purpose of the lab is to show exactly how Poisson's ratio affects these materials and is given by the materials. That shows us and shows a potential engineer how the material will deform under strain. And this is measured in megapascals. Mario will explain how we do this.
Now, the methodology for this lab was very simple. It was a standard tensile testing where the dog bone sample was loaded and tested up to 20 pound, up to 50 pounds force. The only difference was that in this lab, we used the camera to use GOM snap and GOM correlate to digitally see how the material was deforming both both axially and laterally.
So here we can see our first test. This is the polymer deformation slide. We're looking at the millimeter change in length and width as this polymer gets subjected to more force. If we go onto the strain, here we can see the same sample, but we're seeing our percentage of strain, which as we can see, the lateral section on the top has a single node of maximum strain through the center, and then the axial strain shows multiple different points, which is what we would expect. If we go on to the next slide, this is our aluminum deformation. You can see that the aluminum sample we had is a much more compact area, which, as you'll see in the strain, leads to a much less refined definition of where our strain is happening. Here we can see our lateral strain mostly non-existent. We see a little hot spot at one point. Our axial strain, we see basically the entire measurement area lighting up at our maximum point, which is not what we should be seeing. We should be seeing layers. And if we go to the next slide, here we can see our copper deformation. The copper deformation, very predictable. This is not our sample. This was the TA sample. Reason for this, our copper sample was unable to be read in GOM correlate because once we added over 1 foot-pound or a pound force of force, the sample came out of focus and it was no longer able to be used in GOM correlate. If we go to the next slide, though, here we can see our strain in the copper sample, which we see very unusual patterns, not exactly what I was expecting to see, not what the group was expecting to see. We see very small concentrated areas of strain. This is likely due to GOM correlate working in vectored areas, which are determined through a calibration process. That led to us having this strange, like almost tiger striped pattern through certain samples and possibly not getting the most accurate reading, although it seems pretty accurate based on our calculations.
Now, using the previous data, we were able to calculate Poisson's ratio for all three samples, and we will now discuss the meaning of these samples. As you can see in the data, the polymer calculated value for Poisson's ratio was within range, but just on the low end. So it's good data. The only reason it had a 27% error is because we used the median value of a wide range between 0.15 and 0.3 to calculate our percent error, but it's still within the accepted value. Our aluminum sample had nearly double the expected value for Poisson's ratio. And this was, again, like Blake said, because the available section to be able to be analyzed was very, very small. So accurate data taken across the entire gauge sample of the aluminum specimen most of it was unable to be used, and therefore it's very inaccurate data. And the copper Poisson's ratio was just below the range, but still very accurate data and the most accurate sample as it was collected by the TA and done in perfect conditions.
So using the vernier caliper, a camera set up with the computer, a phone to record, we're able to capture the deformation of each sample and compare the samples with already known values throughout the engineering community found in the pamphlets. Using the lateral strain and longitudinal strain, it gives us Passion's ratio, which again shows just a potential engineer what material to use and how it might deform under strain. For future work, we recommend using a suitable source of light. The light we had, we were having trouble just propping it up or holding it where it needed to be, and it reflected off of the copper sample and the aluminum sample way too much. And maybe even next time, try and scuff up the aluminum so you can see better. But yeah, taking time to set up the station is definitely key to accuracy.
Now we got our known accepted values for Poisson's ratio from the following ASTM standards, one just being for standard tensile testing of polymers and the other two being specifically for copper and aluminum. And potential questions that could be asked by an audience that received this presentation would be, why did the aluminum sample have such a high percent error, which Blake will now answer.
That's likely due to the small measurement range that we had due to lighting issues and reflectivity issues with the material, as well as just poor video quality.
And another likely question that would be perfectly normal to ask would be, why did the copper strain graphic seem so consistent, barely changing, and when they did change on a nearly random form?
That's likely due to the material qualities or due to the reflectivity of the material.
Thank you. This is our presentation.